Welcome to our review. So tonight we'll just be going over kind of the first part of the class. Yeah, if you have any questions, let me know. We're going over, so first we're going to go over integrating factor. So you're given just an equation in the form of this, where you have just one derivative plus the function times by a function of t equals to a function of t. And then you are given, then you know that an integrating factor is just e to the integral of the pt dt. And so, yeah, we're just going to use that to solve this problem. If you guys have any questions on it, let me know. However, I'm going to, yeah, I'll just do it right here. We have y prime minus 3y e to the negative t. So your mu of t is, since it's already in this form, we just need to find our mu of t, which is equal to e to the integral of minus 3 dt, which is equal to e to the negative 3t. And then we multiply the entire equation by e to the negative 3t. So y prime minus 3y equals to e to the t. If you were to multiply this out, you'll have y prime e to the negative 3t minus 3 e to the negative 3t y equals to e to the negative 3t e to the t. If you look at this stuff on the left-hand side, this is just the product rule of e to the negative 3t y. Does that make sense? Okay.
That's just like given the chain.
Yes, just the chain rule, yes. Yeah, so if you were to take the derivative of this in terms of t, you would get this. Okay, so then we would have e to the negative 3t y equals to the integral of e to the negative 3t e to the t. This can simplify to e to the negative 2t. Yes, good job. Now, yes. On the right-hand side, because technically we integrated the left-hand side as well to get it into this form, and so we have to integrate both sides. So from your integrating factor, no, yeah, it just, well, you deal because you're saying you'd add a c up here, or yeah, add a c. Yeah, it would technically, this entire process deals with that constant in the last constant. Yeah. So you don't have to use it up there. It also, like, you can, it just adds more stuff to deal with, and it will be dealt with in the end. So, yeah. Okay, so then we have e to the negative 3t y equals negative 1/2 e to the negative 2t. Okay, now we want to get y by itself, so I'm going to multiply everything by e to the 3t to get rid of it on the left-hand side. I have y is equal to negative 1, oh, sorry, I forgot my plus constant there. Negative 1/2 e to the t, because 3t plus, or 3t and negative 2t is just one positive t, plus c e to the 3t. We were given an initial condition to solve for our constant. So now we can just plug that in. So you have y of 0 equals 4. So 4 is equal to negative 1/2 plus c. You can add c over to the other side. So you have 9, oh wait, sorry. Yeah, 9/2 is equal to c. So then our solution would be y equals to negative 1/2 e to the t plus 9/2 e to the 3t. Does that process make sense? Okay. Any questions? Okay. All right. So that was pretty simple. And then our solution is shown here, but I covered it up with my writing, but it's the same thing. All right. I also left a blank side for me to work on it. Okay, now we're gonna go over null and particular solutions, which I am gonna let Andre do.
Hello.
You have to keep this because it connects to the Zoom.
Oh.
Ow. Ow.
What was that? And you guys all zapped me. I guess there's no one on the other side, right? It's just for recording?
Yeah.
Oh. All right. Here's the pen. Okay, so we're gonna do null and particular solution. Give me 1 second. My notes. All right. So if we think about like a bank account, where you have like a certain like lump of money in this bank account, and let's say you get like 3% interest in this bank account, because I think that's the example we're gonna work with. It's like a 3% thing. The amount that the bank account grows every month or every year or whatever is dependent on how big the bank account is. If your bank account has like $10,000 in it and you have 3%, you'll make like $30 per pay period. If it has, I think 30, no, $300, something like that. You'll make some amount of money, but if you have way more in your bank account, you'll make way more in interest. So the null solution in a differential equation represents the amount that your bank account grows depending on what's already in the bank account. The particular solution or your forcing function, or comes from your forcing function, and so like the particular solution kind of represents how much your bank account grows depending on outside factors that aren't the money that's already in your account. So things like if you're like saving $100 and you're saving and investing $100 into your account every month, that's like your forcing function, which represents money added to your account that comes from the outside, which is what your particular solution represents. So your particular solution is money that comes from outside your account that makes the account grow. Your null solution is money that is already inside your account that makes your account grow. How do I make the slides? Is it this? There we go. So mathematically, it looks like this. You can see you have your like a y prime plus b y, but on the right side, your there's no forcing function. You're not changing your account from the outside at all. Your y prime is only dependent on your y prime being the rate your account grows, and your y being the amount of money in your account. And you can see the particular solution looks the same, but now you have a forcing function on the right side. So here's the example that we are going to work with. Let's see. Yeah, go ahead. Okay.
What solution we're trying to get to?
Are you talking about just this? Yeah. So this is your null solution. And this is just when you simplify this differential, or when you solve this differential equation by getting rid of the y prime and putting it in terms of t, this is what it turns into, using the integrating factor that Marley talked about. That's how you would solve that.
Also, this version of the left side is your null equation. You solve that.
Um,
It says 0 on the right side, not the left, right?
yeah, because there's nothing, as you can see, like this is the y prime represents the amount of change that happens to the bank account, and the y prime represents the bank account. And you can see those are the only two things in this whole equation. There's nothing on the right side. So the amount of change in the bank account only depends on what's in the bank account.
The same ODE set the 0 solve.
Yes, yeah, that's in there.
And then particular, same thing, but you just have forcing.
Yeah, which represents some sort of like outside force. Okay. All right, any other questions? Okay. So this is the example we're going to solve. So the first thing that we're going to do is we're going to use the integrating factor to solve our null solution. We're just going to kind of ignore the right-hand side for a little bit. So if we write that down like that, we can do this, and then I'll use the integrating factor. Let's see. I don't remember. I remember I do it in my head kind of. Okay. When we solve using the integrating factor, this differential equation, we get this null solution right here. And then what we can do is we can take this null solution and we're going to plug it back in to, or hold on one second. Oh, I'm sorry. I said that wrong. We know that this particular solution, we know that when we solve this differential equation, that the particular solution is going to kind of resemble itself, resemble the forcing function. So because the forcing function is t squared, we know that our particular solution is going to look something like this. It's going to be a quadratic. So think like a t squared plus b t plus c. And this is true for most forcing functions. We just kind of know what they're going to look like after we've solved for their particular solution, just from like, I don't know, trial and error or grad students working a lot and messing up a lot. And then, yeah, I don't know, however they do that. And so because we know that, we can take this, substitute the coefficients for variables, and then plug it back in to our original differential equation up here. And so what we're going to do is we're going to find xp right here, then, or our particular solution. We're going to find the derivative of our particular solution, and then we're going to plug these back into here. So that looks like 2at plus b when we swap in our particular solution to right here, plus 3 times our particular solution, and that is all equal to t squared. So now we can simplify a little bit. And now what we can do, we can pretend like this right-hand side also has a t and a constant. But in front of the t is a 0, and your constant is a 0. We know that everything on the left side, all the coefficients on the left side that are in front of a t squared, have to add up to all the coefficients on the right side that are in front of a t squared. And so by following this kind of like rule, we can create a system of 3 equations just from this one equation. So first, we can take the 3a that's in front of our t squared right here, and we can set that equal to the 1 that's in front of our t squared right here. And then next, we can look for all the ones that have t, just a t. We can find 2a in front of the t right here, and 3b in front of the t right there. And we can add that, and that we know that that's going to add up to 0. And then we can do the same for the coefficients that don't have a t in front of it, or just the constants, I guess. And so we have a b, and we have a 3c. And we know that is equal to 0. So now we can solve our system of equations. We know a is equal to 1/3. We know 2/3 plus 3b equals 0. So 3b is equal to negative 2/3. B is equal to negative 2/9. Negative 2/9 plus 3c equals 0. 3c is equal to 2/9. C is equal to 2/27. So now we can plug this a, the b, and the c back into our particular solution that we have back here. And we get 1/3 t squared plus, or minus, oh, that's so cool, minus 2/9 t plus 2/27. And we can find our full solution by just adding these two solutions together. So our x is equal to c e to the negative 3t plus 1/3 t squared minus 2/9 t plus 2/27. And that is our full solution using the method of undetermined coefficients. And we could, if we had an initial condition, we might have an initial condition. Oh, no, we don't. If we had an initial condition, we could solve for this constant right here as well. Yes.
Okay. They're linear independent. So you're trying to, if they're, if you're taking the method of superposition of the finals.
Yes. Yes.
Are
I believe so, yeah. I think so. I just know like, well, the null solution just represents the amount that the account grows from what's in it, and the particular solution represents the amount that from the outside forces. And when you just add those together, it just gives you the total change in your account balance. So I think it's been a long time since I took LinDiff, so I think
I could comment on this.
yeah, okay.
Yeah, so the
Okay.
assumption here is that we just know that they are linearly independent. There is a check for it,
Yeah.
but it's a long drawn out process. So we are assuming that they are linearly independent from each other. The
Okay.
homogeneous solution and the particular solution.
Yeah.
Thank you.
All right. Any other questions? Sweet. Will this erase when I get to the next slide? Yes. Okay. Sweet. Okay. Now we're going to talk about delta and Heaviside functions. I'll just get all this on and then talk about it. So the Heaviside function stays at 0. It looks like this right here. And this big T right here will be replaced with some constant. And what happens is that this function stays at 0 until it gets to that constant, and then it jumps to 1 and stays at 1 for infinity. So you can kind of use this to turn a function like on, or yeah, turn a function on after a certain amount of time. So let's say like you have a bank account and you want to model your bank account, like putting $500 in per month into your bank account, but you don't want that to start until 6 months from now. You could use that to you could use the Heaviside function to create a forcing function that doesn't turn on until after 6 months of time have passed. The delta function represents an impulse. So it will stay at 0. And then when it hits that time t, as you can see like right here, when it hits this time t, it'll jump up to infinity for like a split second and then go back to 0 for infinity. And the area under this line right here, this is kind of weird, but the area under that line is 1. So when you put it in an integral, it just kind of takes the function at that point. So if you multiply this by a forcing function, you get an impulse. So let's say you just want to add $500 to your bank account once and then never add anything to it again. You can model that using the delta function, and it will add 500 to your account and won't touch it again. You can see how adding 500 to your account will change the balance of your account over time depending on what time you add that to your account. And yeah, and so these are very useful in differential equations just because you can kind of model time. Since time is a big impact on how differential equations grow, now you can kind of like mess with the time at which your forcing functions operate. Are there any questions? Okay. I'll make sure you guys are all done writing before I move on. All right. Oh, it's this example. Okay. I don't know what this S means. It's just also part of the Heaviside function. I don't think it adds anything. What was it? Yeah, I don't know.
I don't think that should be there because that's
Yeah.
from S space
I don't
with
know.
the Laplace transform.
Yeah, that's what I thought too. It was weird. But anyway, ignore this S. So now we're going to solve this differential equation. We have our left side right here, and then we have our forcing function, which is just this Heaviside function that turns on at t equals 5. So what we're going to do is we're going to use our integrating factor to solve. So I'll do that to this side, multiply our integrating factor over to the other side. Then we'll take integral of both sides. So the bounds of our integral will be 0 because that's when time starts. Time starts at 0 and will go to infinity. And so what this does is this makes it so that the function doesn't turn on until t is equal to 5. So everything before t equals 5, this right-hand side right here is equal to 0. So um, we can remove this and then put 5 in the bottom bound of our integral, because from 0 to 5, it's all equal to 0. And then from 5, that's all equal to 1. So now it's just this function from 5 to infinity. So now we can solve. I didn't put the limit as a approaches infinity. I'm not a math professor. Just don't tell Hevelin I did this. Okay. And e to the negative infinity is just 0. And then right here, this just adds up to 1/3 e to the negative 15th. And so then we can continue going and solving this. And if we were to keep solving it, we would get something else. But I made a mistake on purpose. So if we go back a little bit to before we solved it, we noticed that it asks to evaluate at y is equal to ln of 2. I don't remember off the top of my head what y equals ln of 2 is, but it's definitely less than 5. And so what that means is this right-hand side of this function it hasn't turned on yet at y equals ln of 2. So this right-hand side of this function doesn't matter at all, actually. We wouldn't solve it. Like the solution to this is just you just find the particular solution, which, oh, sorry. It's kind of annoying that the problem's set up like this. I don't make the problem. But it's literally just the particular solution. Or the null solution, yeah, you're right, sorry. And then you just solve it at y is equal to 5, because the forcing function hasn't turned on when ln of 2 happens. Does that make sense to everybody? Yeah, so if this was a bigger number, we could continue going and solving. And so you can kind of see like the process for how you would solve it. Now you have this right-hand side, you just get y by itself and then keep going. But in this case, the answer is just going to be when we solve this. So 5 is equal to c e to the 3 times 0, which is just equal to c. So then y is equal to 5 e to the 3t. Y is equal to 5 e to the 3 ln of 2. And that is, what is that? That's 8 in there, and those cancel out. So y is equal to 40. I feel like that's wrong. Is that not right? Did I mess up somewhere? No, I didn't mess up. Yeah, y is equal to 40. Yeah, that is the answer. Any questions? Okay. Yes, so yeah, so this is yeah. So you kind of get like two differential equations out of this. Like this is the differential equation, or the two equations out of this, regular equations. Like this one, if I were to continue solving it, I could, but I don't want to. This would be what y equals after, like from, yeah, yeah. And then this is the equation you would use for that. Yeah. Okay, and now we'll do the delta function, which is similar. It's just the derivative of the Heaviside function, but if you remember, it's just that impulse. So instead of turning on and staying on, it just takes the function at that time. So, and we aren't even given a differential equation, we're just given this function. So first we'll check to make sure that 5 pi 6 is between negative 25 and infinity, and it is. So we know, and so because it's in there, then what this does is this will just get rid of this integral completely, and then equal this function at this time. If we get out our unit circle, it's 5 pi 6, that's 1, square root of 3, 2 sine of 5 pi 6 would be 1/2 times 2. which is equal to 1, and that's our answer. Does that make sense how that worked? This one's kind of confused me a lot when I was in LinDiff. So if you guys have any questions, feel free to ask. All right, sweet. I have one more topic, and then I don't know why I'm racing. Then other people get to take over. So yeah, you can see this is what it looks like. You can see the function of t is equal to f of big T, which is the big T inside of the delta function, assuming that big T is within your bounds. Okay, so now we're going to go to logistic equations. These are like a certain type of differential equation that represent population growth with like a population cap. So, or like a carrying capacity. 1 second. Okay. So we're given this equation set up and we'll be given, where is it? Here we go. We're given, so usually for these problems, we'll be given like an equations. This is the equation we're given, which is the same as this thing. And so what we're gonna do, and so this represents like the growth of bunnies on an island. So this is like the amount that the bunnies are growing. Y is the number of bunnies on the island. We know our initial condition, or the initial number of bunnies on the island, is 14. And so what we're gonna do first is we're gonna distribute this thing out. And what we're gonna try to do is we're gonna find out what y prime is equal to 0, and that'll let us make a graph that shows how the bunnies population will change depending on the number of bunnies there are. It'll help us find, like, they're called fixed points, and we'll use the fixed points to determine where the bunny population is kind of headed. So if I distribute this, I have it in here. I'm not going to actually do this math. If I distribute this function, I get this. And so we're going to set this equal to 0 to find our fixed points. And so we'll use the quadratic formula to find when y is equal, or when y prime is equal to 0.
We have a question.
Oh, sorry. Yes. No, it's okay. Right now it's good. Who do you have?
It's every chapter.
Well, I mean, Evelyn,
Be like every single one of your chapter tests, just kind of like a few questions from each.
Okay, that's
I,
what he's
I,
doing.
I believe that's gonna be the layout of the final.
Okay, is that what he said? Yeah, that's what he's been saying, it's 2 to 3 questions from each chapter. So, yeah.
that's so nice. That is very nice. Different from, okay, cool. Okay, so now we'll plug the rest of it into the quadratic equation. And when we solve this, you can put it in your calculator if you want. We get y is equal to 9 and 216. So from here, we can make a graph. And we know that we can plot y prime on one axis and y on the other. So this axis kind of represents, like, depending on how many bunnies are on the island, how fast will the population grow? And we know that at y is equal to 9 down here and 216 over here. That at these points, so if there's 9 bunnies on the island, then the rate of bunnies is 0, so the population will just kind of sit here. If there's 216 bunnies on the island, the rate is also 0. The bunnies will sit there. They won't grow or shrink. And so next what we can do is we want to graph the line. We know the 0, so now we're going to graph the line. So we're going to pick a point kind of in between these two numbers, and we'll plug it into our function and see if it's positive or negative. So if I take 100 and I put it in here, you can see this is going to be positive. Like if I were to put 100 right there, that would come out with like 125 over here. And that's 125 times 100. Sorry, I should actually do the math. 125, 125th times 100, 225 minus 100, minus 1944 over 25. Can I borrow your calculator? Okay.
It's in degrees. That's important.
I don't know how to use this. How do I?
What are you trying to do?
1944 divided by 25. So no.
So 1944 divided by 25, is this
Yes.
correct?
Yes. Okay. And we can see after we do all this algebra, or sorry, is there a question? Oh, okay, sorry. Okay. And we can see that this number comes out positive, so we know this function is above here. And we can see there's no double roots or no like this isn't squared or anything, and this isn't squared. So we know that it's going to cross, this line is going to cross the y axis and not bounce back up. So we know our function looks like that. And so now if we think about what happens here, this is the rate of bunnies. This direction is the rate, it represents the rate of change of the bunnies. So if it's above this line, then the bunnies, the population of bunnies, this line is going to be increasing. So we can kind of draw arrows above, on this line, on the part that's above the y-axis in this direction to show that on this section of the graph, the bunnies are increasing. And this is true, this is like vice versa is true for when it's below the graph. They are decreasing. Does everybody understand what I just did with the little arrows? Okay. So if the bunnies are, if the population of the bunnies on the island is below 9, starts below 9, then it will go to 0 because it's going to be decreasing. If the population of the bunnies is above 9, it will keep increasing until it hits 216, and then it would then stop because anything above 216, it's going to go back to 216. We can see right here, if it'll show up, the initial number of bunnies on the island is 14. So if we start at 14, which is like right here somewhere, it's going to increase until it's 216. So the answer as t approaches infinity, how many bunnies are on the island, is 216. Any questions? Sweet. This is, please don't.
Don't shock you. Okay. Just gonna flip this to my hoodie. Sweet. So I am gonna go over Euler's equation and how we can use it solving first order differential equations. So Euler's equation is anything that has an imaginary number in the exponent, you will want to use Euler's equation. And Euler's equation is e to the omega it equals to cosine omega t plus I sine of omega t. This is useful because it is easier to know what cosine and sine do when you have like certain boundary conditions. It's just easier to know what happens with cosine and sine than just an e function. So that's why we use it. It's actually super useful. I use it quite a bit. So we have this example of y plus 4y, y prime plus 4y equals e to the 3 2it. So the first part we're going to solve using the integrating factor again. So your mu, sorry, I zoomed in because I'm left-handed. My mu is equal to e to the 4t. So then I have y e to the 4t equals the integral of 3 e to the 2it e to the 4t. Is it okay to make this jump? Is everyone comfortable with this? Okay, awesome. So then we can combine our like terms up here. So we have y e to the 4t equals the integral of 3 e to the 4 plus 2I t dt. I forgot my dt up here, sorry. Okay, so now we can just integrate this. And we have y equals e to the, 4t, or sorry, y times e to the 4t, y e to the 4t equals to 1 over 4 plus 2i times by 3 e to the 4it, or sorry, 3 e to the, oh my gosh, I'm so sorry, 4 plus 2it, and then plus your constant. Yeah, there we go. Okay. I believe that your constant, let me just make sure that I'm not missing anything in here. So, yeah, that's right. So you can keep your constant if you want, and you probably would be given like an initial condition, equals 4 or something, and then you could solve for your constant. However, for the purpose of showing how the Euler's equation works, I'm just going to not keep my constant. Is that okay? Okay, awesome. So then you have y e to the 4t equals 1 over 4 plus 2i, 3 e to the 4 plus 2i times by t. Okay, now we're going to divide or multiply by the e to the negative 4it, or not I, just 4t. And that will get rid of our this one and this one. So then we'll have y is equal to 1 over 4 plus 2i e to the 2it. And this is what we want to turn into Euler. We want to use Euler's formula to turn into trig. But yeah, actually, before we do that, let's get rid of, we don't want i's on the bottom of our fraction. So let's complete the square to get rid of the I on the bottom. So we would then have y is equal to 1 over 4 plus 2i e to the 2it. And then to complete the square, we want to multiply by 4 minus 2i and 4 minus 2i, top and bottom. So then we would have y is equal to 4 minus 2i divided by, let me just make sure I'm getting my bottom correct. 16 plus 4. So that's 20. Does that make sense why I did that? What's happening there? Okay, awesome. Oh, I hit a number. So then multiply that by e to the 2it. So then you would have y is equal to 4 minus 2i all over your 20. Times by, now we're going to put this into our cosine and sine. So it would be cosine of 2t plus I sine of 2t. Okay. The next step would be to separate your fraction out into 2 separate terms. So you would have, and I'm just going to erase it right here because I'm running out of room. So you would have 4 over 20 minus 2i over 20. And then you're going to want to distribute this out. So you'd have y is equal to, I'm going to simplify this to 1/5. Is that right? Yeah. 1/5 cosine of 2t plus I over 5 sine of 2t. And then you'd have minus 1 or I over 10 cosine 2t. And then because you'd have an I squared, you'd have a plus because you'd end up having another negative, plus 1 over 10 sine 2t. Okay, I am running out of space, so I think oh, I did, sorry. So this whole thing is multiplied by 3. We can distribute that later. And then you can go y is equal to, then you can simplify this and get your terms. So I'm going to keep my 3. And then I'm going to combine my I terms and my not imaginary terms. So I'd have 1/5 cosine 2t plus 1/10 sine 2t. And then put another bracket there, plus my I. And then for my I will have a cosine and a sine term. So I have, where's my I sine? So 1/10. Actually, I'm going to write the other one first because that's negative. I have my 1/5 sine 2t minus 1/10 cosine 2t. I wish I could just move it over, but I don't really know how. So I will just rewrite it on this other page. So my final solution is y is equal to 3 times by 1/5 cosine 2t plus 1/10 sine 2t plus my I times by 1/5 sine 2t minus 1/10 cosine 2t. Okay, so then this would be your real, and this would be your imaginary part to the solution. And if you were given like a boundary condition, or you were given anything that you would want to know what's happening with these functions, it's easier to know what's happening with cosine and sine than it is just to know what's happening with e to the raised to the power. So that's essentially all you have to do with using Euler's equation for first order. Any questions? Okay. Okay, I'm going to give this to Michael and he'll finish up. My iPad.
Shoot.
Oh, I want this pen.
Yeah, it's kind of important, right? Okay. Now, before I start, just you've all been to the EMRC before? Cool. Yeah, if you are not aware of the EMRC, it's kind of like the AMLAC, but it's kind of it has an engineering flavor to it, I guess you could say. We're on the 3rd floor here in room 332. And if you're an engineer and you're struggling with math, come talk to us. Any math, pretty much, that you'll run into in your major. Not any math. All right, let me pull up my slides. Okay, all right, so separable equations. Let's take a moment to remember that with separable equations, on one side, we're going to have something like, we're going to have like a y prime is equal to, and then we're going to have some kind of a function of x, and then we're also going to have a function of y. And why we want to do this as a reminder is so that way we can move the y to the other side and then integrate. So let's apply that with this guy that we have here. So here we have our ODE, and we're thinking to ourselves, well, how can I get it into this form right here? Well, one way that we could do it is we could factor out this 14. So let's do that. We have this y prime is equal to 14 times y squared plus 1. All right, so now we have some function of x, even though x isn't present. And then we also have some function of y. So let's continue and we'll divide out our function of y. So we're going to end up with something like 1 over y squared plus 1 times dy dx is equal to 14. All right, now we're going to integrate with respect to x. So let's do that. So we're going to have integrating 1 over y squared plus 1 dy dx is equal to 14 integral 1 dx. All right, so at this point, we would note that we have the, if we were using some kind of a table of integrals, for example, we would note that we could use a substitution with arctangent here. So I'm going to make that jump right there, and we're going to end up, when we integrate, we're going to have arctan of y over, and let me write down that substitution really quick so that way we're all on the right page. Separable. Yeah. It's going to be y is equal to tan theta. dy is equal to secant squared theta. It's basically a trig substitution, but in the end, it's going to be arctangent of y over 1 plus our constant of integration, which we won't forget, plus 14x plus c2. All right, and let's keep going. So this is going to simplify down to arctangent of y is equal to 14x plus c3, which c3 is just me combining c1 and c2. All right, now let's move that arctangent to the other side through tangent. So we're going to have this y is equal to 14x plus c3, whoops, under tangent is parentheses. Okay. All right, so now we know what y is, but we don't know what c is. And we can solve for c by using our initial condition. So if we were to use that, we would end up with 1 in place of y. And then in place of x, we would have this 0, which would turn this 14x just into 0, and then c3. So what we can do now is we can use arctangent on the other side. Arctangent of 1 is equal to c3. Now we can substitute this arctangent of 1 in place of c3 in our original solution, and we'll have it in the form of y is equal to, let me see, tangent of 14x plus arctangent of 1. Does that make sense? No questions? Okay. We shall move on. Okay. So the next slide's discussing undetermined coefficients, where we'll know that we're running into something like this when we have some second order differential equation and the coefficients in front of y are constants and they're not variables like x or t, for example, in this case. So essentially what we're going to do is we know how to solve for the homogeneous solution on the left side, but what about the right side? This is where we can make an educated guess of what form this particular solution is going to make. So, for example, I believe on the next slide, yes, here we go. If we have on the right side just some sort of polynomial, this would be our guess. So like if, for example, we had, I don't know, let's say 36t, we would assume that our guess would be that y particular is equal to a t plus c. And it could also take the form of exponentials as we've seen in the previous slides. And then here is the really tricky part, is when we have some kind of sinusoids. The key to remember with these is that even if you have, like, let's say 6 sine of, like, I don't know, 2t, in your guess that you're going to make for what the particular solution will be, you have to use both sine and cosine. So our guess will take the form of A cosine of 2t plus B sine 2t. Okay. And then this, the product is when you are going to have multiple of these forms in one particular solution. All right, so let's look at, oh yeah, of course. Kind of jumping the gun a little bit here. Yes. Are we good to go to the next slide?
Yeah.
Okay. Yeah, I think all of this is a lot of mumbo jumbo, but let's look at an example. We'll do really quick. So here's an example. We look at the right side, and we have some exponentials. So when we get to our y particular, we'll know that that's what our guess is going to need to have in it. But first, before we do that, let's start with our homogeneous solution. So we'll start with this left side. So we're going to have y prime double prime is plus 9y is equal to 0. And we will form the characteristic equation with this. So r squared plus 9 is equal to 0. Now we just need to find our roots. Now, luckily, this is fairly simple here for this example. We're going to move that 9 to the other side. We're going to have a minus 9. And then we'll take the square root. And don't forget, plus or minus. And then we're going to have square root of minus 9. Now, what this means is because we have this minus sign under the square root, we're going to have the worst. It's going to be complex roots. So our roots are going to be of the form plus or minus 3i. And much like how we had here, we're going to have this a cosine omega t, b cos. Wait, why are those both cosine? This one should be sine. Whoops. We're going to have that same situation here, except that omega is going to be 3. So our y, homogeneous or null, whichever term you prefer, is going to be this a cosine of 3t plus b sine of 3t. Okay. All right, so that's our homogeneous solution. And let's move on to our particular solution. So earlier we had a guess that it should be of the form, let's say, y particular should be, and this is our guess, we just happen to be really good at guessing, that it is going to be, let's use a new variable, c, e to the 2t. All right, so that's going to be our guess. So we're going to now take the derivative twice, and then we'll have all the components so we can plug it into y double prime and 9y. So let's do that. So we're going to have y prime is equal to 2c e to the 2t. Y double prime is equal to 4c e to the 2t. Now let's substitute these values in, and let's go from there. So we're going to have this 4c e to the 2t plus, and then we're just going to have 9 times c e to the 2t is equal to 52 e to the 2t. And I'm saying 2t too many times. All right, so let's simplify this a little bit and see if we can figure out what our constant is. So let's get rid of these guys, and we're going to have this 4c plus 9c is equal to 52c. Now I see too many zingers right after each other, right, guys? All right. When we simplify it, we're going to find out that c is 4. And let me just double check. We got to verify it with the computer. Yep, all right. Quick maths right there. Now we know what c is, and we can plug that into our particular solution right there. So that will be of the form y particular is equal to 4 e to the 2t. Now we can finally form our general solution. And as a reminder of the general solution, oops, I'm not going to write general. That's a little long. I'm just going to do this. Is going to be y, and then it's going to be null or homogeneous, whichever you prefer to call it, plus the particular solution. So we know both of these. So it's going to be y of t is equal to this a cosine of 3t plus b sine of 3t. And then we're going to add our particular solution right there, and plus 4e to the 2t. Okay, and that would be our solution. Do you guys have any questions? Okay, cool. Now, earlier one of you was asking about whether they're linearly independent or not. If you guys want to explore that in the future, just come by the EMRC and ask us to explain the Wronskian, which is the check that you can do to ensure that these two solutions are linearly independent. Yep. Okay. Let's move on to the next. Wait a second. Oh yeah, this one has a solution. And what do you know? We did it. We got the right one. Oh man, I'm so good at this. Yep. Totally didn't rehearse this beforehand. First time. All right, so now we have a much trickier example that's longer, way longer, with this sinusoid on the right side. Let's save our guess until after we've figured out what the homogeneous solution is. So let's start with that. I'm just going to jump right into it, where we're going to have this r squared minus 6r plus 9 is equal to 0. Does anybody want to venture a guess on what our roots will be? A repeated root of 3, yes, exactly. Ta-da! So our roots are going to be 3, 3. I just write this long form just to remind myself of this. So y homogeneous is going to be of the form a e to the 3t. So does anybody want to also venture a guess on what our next component is going to be? What is this going to be, given that we have repeated roots? Exactly. You are 100% correct there. We're going to have, for each repeated root, you will have a multiple of t. But that is only true when we have these constants as our coefficients. If you have variables, it is different. That's where you're going to have variation of parameters, but that's a whole nother topic. That's so much fun. I know you guys can hardly stand waiting for the explanation for that. Is that tomorrow? Yes. So like for this one. Yes. So like let's say, oh, I should write. I have a digital whiteboard right here. I will use that. So like imagine if we had a y prime in here, and for some stroke of luck, we found that our r's are 3, 3, and also another 3. Like you said, we would have a e to the 3t plus b t e to the 3t, and then plus c t squared e to the 3t. Okay. Does anybody else have any more questions? All right. Okay, let's continue. So we have this e to the 3t right there. Okay, now we know our homogeneous solution. Now we got to tackle with this sinusoid that is, oh, so much fun. So we know that sine and cosine, like birds of a feather, stick together. So they both have to be in our guess. So we're going to guess that it's going to be of the form, let's say, y particular is going to be equal to, I need to use some different letters. So maybe let's do, I don't know, d cosine of 6t and e sine of 6t. That's going to be my guess. And much like what we did before, I'm going to take the derivative of that twice. Oh boy, so much fun. Okay, so y prime is equal to negative 6d sine of 6t plus 6e, cosine of 6t. And then now the second derivative is going to be equal to minus 36d cosine of 6t minus 36e sine of 6t. Is everybody up to this point? Everybody understand? Okay, cool. All right, so now let's substitute these into this equation. It's going to be massive. Let me see. So we're going to have minus 36 d cosine of 6t. Let me see. Minus 36e sine of 6t minus 6y prime. So let's think. We have this minus 6 here, and we're going to times it by 6. We're going to have yes, positive 36. Very good. Positive 36d sine 6t. And then for this next one, we have a positive, so it's going to be negative. What?
Oh, no, sorry. You're good.
Ooh, whoops. Oh no, I'm messing up. I'm throwing it. Let me see this e. Dang it. Okay, e. Whoops, it disappeared. Okay, let me see. Cosine of 6t. Let me move this guy up here. Okay. And then we have 9. So this is going to be just simply 9d cosine of 6t plus 9e sine of 6t is equal to 25 sine of 6t. And we barely got it in there. Okay. That's a lot of stuff on there. It looks horrible. Absolutely massive amount of things. So let's see if we can organize it. So we're going to want to form a matrix or even just two equations from where one is all of our cosine terms and the other is all of our sine terms. So let's see, we have our cosine here. This is minus 36d. The next one appears here, minus 36e. And then this next one is plus 9d. We don't have any cosine terms on the right side, so that will be equal to 0. All right, now let's move on to sine. So we're going to have minus 36e plus 36d plus 9e. But we do have a sine term on the other side, and that's equal to 25. Now, at this point, we can just use algebra and figure out the solution, which should be, let me see, let's do that together. So I'm going to have, let me see, so this is going to be minus 27. D is equal to 36e, which is going to be minus 27 over 36d is equal to e. Now we're going to substitute this over here into this guy. And we're going to do that just below here. So we're going to have minus 36e, but e is this minus 27 over 36d plus 36d plus 9 times minus 27 over 36d is equal to 25. Okay, so we do a little bit of simplifications here. We're going to have a 27d plus 36d. And then this is going to be a minus 27 over 4. D equals 25. And when we plug this into the calculator, we're going to find that this d equals 4 over 9. And if you wanted to finish out if you wanted to do this part instead of jumping straight to it, the derivation is left to the user for enjoyment. You know, we all just love doing arithmetic, it's so much fun. Anyway, so now we're going to substitute this guy back into right here. so we can figure out what E is. And when we do that, we're going to find out that, wow, E is minus 1/3. Now, at long last, we can finally build our general solution with a twist. We'll get there. I'm not going to rewrite everything else because you guys saw it last time. So let me see. We're going to have this, let me see, A e to the 3t plus B t e to the 3t. And then we're going to have, let me see, where on earth is it? It's over here, particular. So D is plus 4/9 cosine of 6t minus 1/3, well, that 3 is horrible, sine of 6t. Okay, and if we had some initial conditions, we could solve for A and B, but at this point, since we don't, we're good. Does anybody have any questions? No? Okay. And let's see if we, whoops, if we made it. Yes, as you can see, this took a couple PowerPoint to figure out, and ta-da, we did it. Okay, yes. And this is going to be a shameless plug, but we do have a website which has a lot of useful resources. We cover Calc 1, 2, 3, ordinary differential equations, and let me see what else is on there. There's a ton of useful stuff. You could go check there, or you could come talk to us. We do like both of those options. So I'm just going to go through this. Let's see. Okay, yes. So let me see. Yes, so here we just have the definition of the Laplace transform just for reference. So here's an example of it in use. It's really long, so I'm just going to click through this and stop me if you have any questions. So here we have this ODE that's x prime, a double prime plus 3x prime plus 2x equals 0. This is kind of a simple problem since we don't have a forcing function on the right side, since we're just doing this as an example. With two initial conditions. So the first step that we're going to do is we're going to apply the Laplace transform to both sides, where the Laplace transform is 0 is just 0. And then for this other side, we're going to have, oh, actually before, just pretend you didn't see that. If anybody were to venture a guess of what the Laplace transform of this guy is, what would you say? So Laplace transform of x double prime, what might that be? S squared, okay. Okay, so capital X. So that's the thing is, when, just as a quick reminder, when it's something vague like lowercase x, that just turns into capital X. But it's missing, because we just assume it's there, that it's in S space. And the other one is in T space. But anyways, so S squared X and? Oh no, that's all right. It's a lot. It's a lot. This is going to be minus S times our initial condition of y at 0 minus y prime at 0. That's going to be that first guy. And notice for this next one, it's going to follow that same pattern. So we're going to have plus, whoa, that 3 is horrible. Plus 3. For the y prime, it's going to be the same dealio. We're going to have s, not s squared times x, minus simply y at 0. And then plus 2 capital X. And let's see if I got that right. Wow, I am on a roll today. I ought to pat myself on the back. I do a great job. Okay, so there's that.
Same,
Mhm.
the same power order.
Yep.
Back on the initial condition times you give an S, then the Y. If you have higher orders, it goes Y, Y prime, Y double prime, Y triple prime, right?
Yeah, well, let's see. What if we had y triple prime for, just as a little bit of practice. So if we were to apply the Laplace transform to this, we would have, like you said, this would follow the same power as that x, and then be capital X minus, and notice the pattern here. We're going to have s squared y at 0 minus s y prime at 0 minus y double prime at 0. So it's kind of in this descending order with S, where it starts with the highest order, with 3, and then it goes down until here you could say S is there, but it's to the power of 0, so it's 1. Does that answer your question?
Yep, that's what.
Perfect. Yeah, you were right on the money with that one. Okay, so now that we have this monstrosity, we're going to start to simplify it, which we can because one of our initial conditions is 0. This is my favorite number is now 0. It used to be 2, but now it's 0 for this one reason where it makes everything easy. Any equation is easy if you plug in 0 because it's 0. That's why I love 0. Okay, so as you can see here, we're going to simplify it, and then we're going to bundle up all of the coefficients of capital X, and then we're going to divide them out to the other side. And notice how this guy mimics the same, let's go back here, the same powers that we had in our original equation. That's why this is, I think it's still called the characteristic equation, but it's in S space. So the reciprocal of the characteristic equation in S space is going to be our transfer function H. Okay, my voice is getting dry. Oh, let me get rid of this. Okay, yes, and if you have questions about partial fraction decomposition, because there's so many ways to do it, we have, shameless plug, a page about it on the website that's really good. So we're going to use that here because we have this irreducible quadratic, I believe it is called, and we're going to use a strategy where once we have partial fraction decomposition completed, and it's in A and B right there, we can now solve for A and B, whichever way you fancy. In this way, you could set S to be a value and then solve for A and B. There's quite a few ways to solve for the constants, but I'm just going to skip ahead because these take a while, the Laplace transform problems. Okay, so the end goal is to go from this monstrosity that looks horrible, that looks nothing like any of the Laplace transforms on our table of Laplace transforms, into something, into something like this. Oh yeah, this we can work with. Yeah, this is magnificent. Oh wait, whoops, I went a little bit too far. So yeah, we'll notice here that this will match a template on your table of Laplace transforms, as you can see here, where we have essentially -1 as our corresponding to this value here for S. Let me see. And so, yes, this would be the solution right here. Let me see, I think. Is this just another example? It is. Before we move on, does anybody have any questions relating to this one? Is it all right move on to the next one? Okay, cool. Now this is where things get crazy. We're getting crazy in here. Who knew that could happen with math? But it is about to go down because we have this guy right here. This is horrible. It takes so long with some of the other strategies, but we have the Laplace transform, bestowed upon us by one of the math gods, Laplace. So we're going to do what we did with the last one is we're going to apply the Laplace transform to, whoops. Oh, you know what? Pretend you didn't see that. Keep skipping ahead, trying to go fast. If we were to apply the Laplace transform to this guy, what would that be? Pretending you didn't see that slide. And
It's gonna take me a minute.
oh, no worries. Because this is not a test, we don't want this low pressure here. So as you can see right here, which I'll erase it, that's what it would be. And luckily my arrow points straight to it. Wow, that's convenient. So here we go. We just have that's the difference. If you were to remember anything comparing the two Laplace transforms of the sinusoids, is that sine is going to have that constant on top, and cosine is going to have an s on top instead. So using this fantastic knowledge that we just gained, we're going to put it right there. And much how we did last time, we're going to try and simplify things a bit. And this is even better because now, oh my goodness, look at that. My favorite number appeared twice. Wait, Amalek Tutor, is that controversial to say that 0 is a number? Wait, don't answer that. Okay, anyways, continue.
I like 0. I'm an engineer.
Wait, you are?
Yeah.
And you work for the Amalek? It's enemy territory. I'm just kidding. We'll cover the mic. I'm just kidding.
Secret spy. Don't worry.
Anyway, so we simplified a bit. Oh, wow, this is perfect. I can X this out, X this out. Oh, man, this is just magnificent. So we're just going to be left with this guy, and this guy, which will turn into whoop, this guy right there. Perfect, huh? So now that we have that, we're going to do what we did last time. We're going to factor out this capital X right here and form, ta-da, wait, whoops. Ta-da, well, they skipped it. Or maybe they didn't. I'm too lazy to check. So let me see. So yeah, it's going to be x squared plus 5s plus 6. And then they're going to divide it out and go to the other side. Yep, very handy right there. Okay. Does everybody remember what these components are of
Sine 4t on the. No, cosine.
this is a little different where like at this point when we're trying to find the solution to it would be lowercase x. What this as it is right now, this is the transfer function which transfers the inputs out that you put into the system. It transfers them to the outputs. And this is going to be just the Laplace transform of your forcing function, yes. Does that make sense to everybody? Because I know that they probably don't talk about what, like, because that actually has a name. It's called Duhamel's principle. So let's keep moving on. So luckily, we can find we don't have to do partial fraction. Oh, wait, actually, no, we do. I forgot. Oh, yeah. Who would have thought we would have a problem without it? You know, it's just our favorite thing is doing partial fraction decomposition. So yeah, just a quick note. Remember when we have something like this where we got this s squared, we're going to need another s term on the top. So we're going to do that. This is the reason why I'm just clicking through the answers here because this one is incredibly long because of this matrix that we have to work with here. So yes, we're going to have our constant term, which would be this guy right here. I usually denote it with a pound sign. We're going to have an s. We're going to have an s squared and s cubed. And as you can see, the only s that we have is just this guy. So we're going to have this one here. Does it make sense how we set this up? Because I know we're kind of skimming through this. Okay, cool. Yes, solve for it. Hopefully you don't get something like this on an exam because I know I would probably miss a minus sign somewhere or end up with a horrible fraction that not even the professor would want to grade. Anyway, so yeah, look at this. This is the worst thing ever. I mean, look at this 13. It's just right there. It's the worst number. So we're going to end up with this. Oh, perfect. These are in forms that we know of. Now, here we know what this guy is, and we also know what this guy is because we can just separate those out. So like we're going to find here, we're going to have, like you mentioned earlier, we're going to have a cosine term, and we're going to have a sine term as well. So sometimes you might have to move things around to kind of, let me see, yeah, everything's moving around just fine. Yes, that should be, not there, should be. Okay, all right. Yes, so here it talks about one of the nuances when you have, let me see, the C was a 1. Yes, when you have an incorrect value. So as you remember from before, for the Laplace transform, or wait, for reverse Laplace transform, we're looking for something like this, where we had alpha over s squared plus alpha squared. Well, the problem is we have a 1 right here, which is not going to work. Does it make sense why we can just add this 2 over 2 out of nowhere?
Yeah, you're taking 4 for alpha.
Yeah, so basically this is, like you mentioned, this is just this. But the problem is this 1 is not a 2. So that's where this guy comes into, because this is just 1, you know? We can multiply as many 1s as we want. So we can effectively plug this guy in right here. We didn't cheat. I know it looks like cheating. Cross my heart. This is probably here, I guess. I'm an engineer. I'm not in medical stuff. So yeah, this 2 will go in there. It's not cheating. And that's how we can make this, force this to conform to this, which is what we want. So we're going to find that out. Ah, look at that. Perfect. And we just multiply this 2 over times that 26, and that's how we get this 52. And wabam, whoop, that's how we get this guy. This would be our general solution. Does that make sense? Do you guys have any questions? Yes, sadly, that is the fate of the Laplace transform. It's horrible, unless it's clean, and then you're just, oh, it's magnificent. But it rarely is. All right, so now we're going to go on to everybody's favorite thing, which are springs. I'm not sure what comments I could add. Maybe, boing. I thought that would get more laughter, but okay. Oh yeah, I do. Okay. So just as a reminder, so when we have springs, we're going to be looking for something of, oh my gosh, I keep pushing this thing down. We're going to be looking for something in this form right here. This is going to be our template that we're going to really be leveraging a lot in this kind of a problem here. So if we go back here, what is our M? So actually, I should write it here. M y double prime plus this guy that we're going, I won't tell you what it is because you got to tell me. Let me see. Whoops. It's a K, yes. Okay, so what is our M in this case? Exactly, it is the mass. Oh, wait, why did I write mass? We already know what it is. 94 kilograms. Being American, seeing kilograms is a problem for me. I'd actually prefer the better unit in cheeseburgers, but we'll go with kilograms. Okay. Now, do we know what is this K called? The spring constant. Exactly, it's a spring constant, and we know what this guy, which is 426. It was minus 6 away from one of the greatest numbers ever. Anyways, so let me see. Do we know what this guy is yet? Correct, but do we have a value for it yet? Exactly. So let me see. Where does it say? Does it say? And we'll get to that in a second. Okay, we're also going to have 2 of these guys. What is our first value here? At 0, what is y? It's exactly. And then for our y prime, what is that going to be?
Or no.
Oh, well, that's a good catch. I almost caught you lacking right there with the numbers. Okay. All right, cool. As a spoiler, we have to find this guy. Let me see. But luckily, yes, here we go. So, ta-da, we actually got it right. Erase this guy. We don't need that anymore. Holy crap, it's 6:30. Okay, so yes. So one of the conditions that we have is that we know it is critically damped. Is everybody comfortable with critically damped, underdamped, and overdamped? Yes? Okay, cool. So we'll just click through this really quickly and for the sake of time. So luckily we can, that portion of the quadratic formula that this is a part of, that is what determines whether it's critically damped, underdamped, or overdamped. We set it equal to 0 because that's the condition that produces critically damped. And we can use this to solve for our, let me see, for the dampening factor. So we will find that to be 400.22 approximately. Okay. Any questions thus far? No? Okay. So now that we have our damping factor value found, we now can construct our ODE because we know what all the constants are. Now we can kind of follow the same shenanigans that we've been doing this whole time, using our initial conditions as well as we can now find the roots. And we only found this one because it's critically damped. So what does that mean? If we only have this guy, what does that mean? Exactly, yes, we're going to have a repeated root, and it's just going to be that same minus 2.13. And we're going to plug that back in, and then we'll solve for our constants. Luckily, one of them is 0, which, oh my gosh, favorite number ever. Makes everything so much more simple. And then the other one is going to be this 28, as we see here. Okay, now we got to get back to the original question, which back here, we found it to be calculate the maximum displacement from equilibrium that the spring is compressed. Assume equilibrium is the origin. So we come over here, and we know that when the acceleration is 0, right, Andre? You're paying attention, right?
Yes.
I'm just kidding. Just messing with you. That would be the condition where we're having max displacement. So what we're going to do, so we have found our constants, we found our roots, and now we can now we can use that to kind of solve for y prime here. So back with our original, which was something to the form of, let me see, t e to the rt, we just, because that was y, we just take the derivative of this. Don't forget to use product rule there. And that's how we end up with, whoops, with this guy. Oh, wait, no, whoops, wrong. I'm blind. I'm wearing glasses, yet I'm blind. Wow. Who would have thought I maybe need to get new glasses or more glasses? All right. So here we go. So here is this. Now we set it equal to 0, and then we will solve for t. Yes. Yes. So we can divide out that the RT. Let me get rid of that to show that. And we're going to find that RT is going to be equal to 0.470. And we can just plug that back into our original equation. And we'll find that there is our maximum displacement. Bam. Just like that. We have accomplished so much as a team, haven't we? And there we go. There's our feedback.
With that, in your equation, I think I understand this is your solution that you did for the e to the RT, well, ER, that's the displacement, and then you're taking the derivative.
Yes.
To velocity.
Yes. Oh, yes. So I was wrong. It wasn't acceleration, it is velocity. Whoops. Yeah. The second derivative is acceleration. So yes, you are correct. I misspoke there. So yes, when it is 0 velocity. Yes. Yep. Which makes sense because as a spring oscillates, there will be a point where it will effectively stop moving for a split second, and that is when it is at its furthest displacement. Does that make sense? Okay. Does anybody have any further questions? Cool. All right.